Welcome to the New York City Category Theory Seminar. For this week we got one of our own, Ray Puzio. Ray, take it away.
Yes, so title of the talk is Uniqueness of Classical Retrodiction, and I will start by defining the term.
Right.
So I'm Raymond Puzio. So I was born in Passaic, New Jersey. I was an undergraduate at Columbia, and one of the highlights of that was that I briefly got introduced to Sam Eilenberg himself.
Oh my God.
Once, same time Jay Stolzberger was there at the Arnold seminar. It was
Yes,
up by Arnold, in fact. So Jay,
I remember meeting Arnold, but I don't remember going to any seminar.
So somehow all three of us wound up meeting then.
Well, that's great.
Eilenberg's no longer here, Jay is. Then I was a graduate student at Yale, and then after a big random walk through a lot of places, I made it, the long way from Connecticut back to New Jersey, and I'm still in Passaic, New Jersey, and with you tonight.
Great.
So I guess
I appreciate that your life commutes.
Yeah, yeah. Well, in fact, right. So it closes, and there's some kind of stew cell here. So, all right. So now to the topic of tonight's talk. So, as I said, first I should say what retrodiction is. So we'll start with something you all know, which is prediction. So a good example of that would be, a weather report. So maybe a meteorologist comes along, he has a look at, here's the pressure on the barometer, the, wind speed, looks at the chart, and then based on that makes a prediction that there'll be a rain starting to, that the storm will come tomorrow night. That's a prediction. Retrodiction, well, what's that? Well, let's say it is a dark and stormy night, and the butler is now lying in his office in a pool of his own blood. Sherlock Holmes comes along. He has a look, he notices, notices there's a window open and an envelope in a suspicious place close to the window. And from that, he makes a retrodiction that the butler did it to himself.
Mm-hmm.
Now, obviously, so that's what I mean by retrodiction. So prediction is when given some set of facts, I, say what will happen in the future. Retrodiction is given a set of facts, I infer what must have happened in the past.
Mm-hmm.
Now, the thing is that usually this is not a certain business. As you know, you see weather reports, at best they'll give you probabilities, they won't say it's definitely going to storm tonight, maybe they'll say it's an 85% probability of a storm. And likewise with retrodiction, usually you might, it's not the way it happens in detective novels, but you might say, well, I'd say, I'm 95% certain that the butler did it. But have 5% not. So how would you, go about computing? Well, the usual way it's done is using Bayes' rule. So just to remind you, so first of all, before I do it, let's say with the predictions, obviously, if it's probabilistic, that means I should have, to describe the process of prediction, I use conditional probabilities. So for example, if I want to predict the storm, well, I should have, probability, say, of the storm, given, whatever it was, the barometric pressure, and whatever variables. So look at a conditional probability. And now, in retrodiction, what I want to do is say, I want a conditional probability of something, that happened in the past, given the present. And that's awkward to think about, so one often uses Bayes' rule, which is a way of sort of reversing the conditions. So, as you know, what does that Bayes' rule look like? Well, so it gives me the probability of B given A in terms of A given B multiplied by this ratio of probability of B to probability of A. All right, so just an elementary identity. And in fact, I'm going to put indices because I might have multiple events I'm dealing with. So for example, in the example here, it might be, B1 might be the butler did it, B2 might be the burglar did it. And A would be the clues. All right, so B had J, A had an I. And of course, I also have, I'll write one more trivial identity. Let's see, probability of is that the probability of event A is probability condition on B happening, summed over all the probabilities of the B's. So to get a retrodiction, means I want to give you this probability of what is the probability of something having happened in the past given the evidence I see now. And so the point is, using this formula, I can invert it and say, well, assume each possible scenario. Assume the butler did it. Then what would be the probability of, finding the envelope where I did it? If the burglar did it, what would be the probability? And then I also assume prior probabilities, if I didn't have this evidence, what would they be? And then I just use this formula to compute it. So that is, retrodiction, or we call classical, or I'm calling in this talk classical retrodiction. Why is that? Well, about a year ago, Arthur Parzygnat came. He was here at this category seminar, and then later gave another talk at our Topology, Geometry, and Physics seminar. And what he was interested in was finding an analog of this Bayes rule or retrodiction for quantum mechanics. So basically, quantum mechanics usually thinks that, well, it's a different probability calculus. Some probability calculus uses complex numbers as opposed to the usual real one we have here. And so what he did was, his idea was, so the problem he was set out was that people had, proposed in the literature multiple ways of generalizing Bayes' rule to quantum mechanics. So his idea was, can I find some way of identifying which is the correct one? And the way he did it was by noticing that if I take, the Bayes rule, it satisfies some algebraic properties, which I'll write down in a moment. And he further noticed that those algebraic properties, they all are general enough that they make sense in the quantum setting. And of all the definitions that were given, only one definition by Petz actually satisfies those conditions. So he said, based on that, he proposed, well, this would be the correct generalization of Bayes' rule to quantum mechanics. Now, he also conjectured that, in fact, it's not just going to be the suggestions that were made in the literature, but of all possible definitions. Namely, that given these algebraic properties, there is a unique thing that satisfies it, which is Petz's rule. As a special case of that, it would mean that given his algebraic properties, there is a Bayes rule is the only thing that satisfies them. And so what I'm going to do today is prove the thing for Bayes rule. That is, I'm not going to say about quantum mechanics. I don't know about that, but I have managed to prove that the conjecture he had that this set of algebraic axioms uniquely satisfies Bayes' rule.
Nice.
All right, so now let me write down the axioms. Well, before I do the axioms, let me just do a little bit of setup. So this is a category theory seminar, so I better show you a category. If all I do is keep talking about detective stories, you'll wonder what I'm doing. So, so a category we'll have two categories. First, we'll start with a category whose of probability distributions. So an object in there is a sample space. And for the purposes of this talk, I will just deal with finite samples. So there'll be no sigma algebras, nothing of the sort, just simple finite sample spaces. All right, so object will be a finite sample space. So that's just it's just a set of outcomes. All right, so just a set. Set. All right. But on this set, we will consider probability distributions. And so, many ways of doing this, but the simplest way, so what is a probability distribution? Well, if I have a set S, I can describe a distribution as a map that assigns, well, to each element a set of probabilities, such as so assigns a number between, in the interval from 0 to 1, a real number, right? And it also has the property that all those probabilities should sum to 1. So we have a normalized probability distribution, all the probabilities add up to 1. So that's an object. Now morphism, basically I'm gonna get morphisms basically using conditional probabilities. So suppose I have a matrix of, so suppose I have two such objects, two such sets, and let's say in this case the A's range over one set and the B's are ranging over the other set. All right, so then, morphism is going to be a matrix of conditional probabilities. And just as here, it acts on, given one object and a morphism. I say it's a morphism from this, maps each distribution to another. But I'm considering them as, so that's one category. Now, however, for the purpose of this, you see, in Bayes' theorem, we had these, a particular probability distribution chosen on one set and a particular distribution on the other. So what I want to do is actually, instead, I'm going to consider a variant in this category, which is sort of a pointed version, where an object will now consist of a sample space with a probability distribution on that sample space. So I'll call that, okay, I'll go over here. So first of all, following Arthur's notation, I call that category C states, so C for classical states. I think I forget. Let me see. Not important, but just to be entirely consistent with myself, I wrote it with a big S. All right. And so the objects there again, too small, consists of I said sample space with a particular probability distribution on that space. And then a morphism, well, it's the same thing, but it must obviously map the preferred distribution on one to the preferred distribution on the other. So again, it's going to be, a matrix, but I want to make sure that if I say this goes from, so I not only want a matrix that, maps the set S, that has an S1 by S2 size matrix, but I want it to map D1, the preferred distribution D1 into the preferred distribution D2. All right. So
what does that mean? MD1 equals D2?
Oh, I'm sorry. So M is so I should say, yeah. So what I mean that is, let's put it this way. M, is going to be, let me spell it out one more way. So it's a matrix, so it's a map, if you like, from R to the R to the S2. But then inside of RS1, I got this distribution. So think the probability distribution vector. So all I want to say is, well, it better send whatever the distinguished probability distribution was on the domain to the one that I picked on the preferred distribution on the codomain. So it's just a matrix from linear map from RDS1 to RDS2, and it sends D1 to D2. And as a linear map, furthermore, it shouldn't be an arbitrary one, but it has to be, it has to have the property of well, first of all, it has to preserve the normalization. So in other words, if this is so normalization, I mean if the things add up to 1 on here, after I act on it with M, I always get a probability distribution. So they have to add up to 1. And furthermore, it has to have all positive entries. So in fact, those are the other two conditions. So I should say that, so M preserves generalization. So that normals it preserves that condition. And then I want all the components of M to be non-negative. And if that's some to 1, they'll have to be in between 0 and 1. Which is just what I want. Obviously, if I said these are conditional probabilities, they'd better, be the right, they better be positive real numbers. So that's my category. All right, now, so what is Bayes' rule? Well, you can, all right, so you can see that what does Bayes' rule do? It took, given two such sample spaces and a probability, if I had two such sample spaces, a probability 1, a probability other, and a matrix going one way, it gave me a matrix going the other way. All right? So, in fact, let me just, all right, so yeah, so let me put it this, okay. So then, let me just, so let me first put a little notation, then I'll get back to saying it in category theory terms. So, all right, so the notation I'm going to make is, so for the output of Bayes' rule or retrodiction is, let me use the notation. So if I have, as I did there, a matrix M that went from, I guess it was A, would say D1, okay. In fact, I'll just call it this way. So I'll just use the letter alpha to stand for the preferred, set A, preferred probability distribution alpha on it. And let's add one of these things that send it to B. Yeah.
Just a dumb comment. Are you saying prior and posterior?
Well, yeah, one of these would be prior, yeah.
Okay.
Yeah, statistician's terminology, I'd call this the prior, not the posterior distribution. So, suppose I'm given such a thing, then what Bayes' rule gives me is something in the opposite direction from the posterior back to the prior. And the notation for it, if I didn't make, so I'm going to call it that, or I guess, let me see, I should call it, no, okay, fine. Sorry, let me just make sure, let me just quickly check for my, yep, AB, good, alpha E. So I'm just going to call that thing that comes out of Bayes' rule R alpha M. So it's just given by that formula I had on the other panel and just a notation for it. So I don't have to write the full Bayes' rule out every time. Now, so now the question is, what are some properties of this? Well, first thing we might, since the category theory seminar, it better be a functor at least. Or what am I doing up here? And it is. So all that means is that, so let's first all write what that means. Let me just get this thing correctly. So, yeah, okay, in fact, just follow. So I'm following the notation. I have my notes. These are, by the way, the notes that I posted in online where we have the announcement for the seminar. There's a little link, and I put a file of these. So this is a preprint. So the proof is complete. I checked it, but I haven't, but it still needs a little work before it comes to preprint, let alone a publication. So everything has been meticulously checked. It just needs some exposition to make it readable. Now it's all right. So. So what this is basically, so it says that if I have a composition of things, so I went from, let's say, a space A to, a space B to a sample space C, first by using, say, a map E, then, map of conditional probabilities F, then if I took the composition of them and I invert it using Bayes' rule, that's the same as, using Bayes' rule on each one and composing them. And basically that follows because what does the Bayes' rule, look like? Well, basically I just transposed my matrix and I rescaled it somehow. So that's gonna, transposition, so that algebraic operation is certainly, going to respect composition.
What is R what is the domain and codomain?
Oh, it's
R
from
as a-
B to A
No, as a functor.
as a functor. It's from C states, so it's a contravariant functor, so you could say it's from opposite of C states to C states. So
Right.
contravariant endofunctor. So yes. Let me write that down here.
Is it dagger?
And the reason for it being contravariant is because in the Bayes rule we transpose the matrix, so that shifts the order of multiplications. Alright. So that's one property, so it's a functor. Alright. Now, there's another property that intuitively makes sense. Suppose that, one were absolutely, suppose that your matrix M or E, whatever I call it, yeah, okay, fine. Your matrix had all zeros and ones in it. In other words, given any event, I knew with 100% probability or whatever, so it was deterministic. Well, then clearly, retrodiction I would expect should just be, just taking the inverse of that function. All right? And in fact, if you look in Bayes' rule, that's trivially the case. If my matrix of probabilities has, if the conditional probability is 100% for one outcome and 0 for the others, of course, if I transpose it, that just means, therefore I was absolutely sure that it would, that having high pressure today gave me rain tomorrow, then I better predict, if I see high pressure, I predict with 100% probability, and if I retrodict it similar, I wouldn't have any room for doubt. So better agree with that. All right, so let's just say so in fact, let's write it this way, from, square matrix like this with 0 on 1s, its inverse is going to be basically a permutation matrix.
You want B there?
No, I want it to be the same,
Oh.
same A, or at least the same size. So I want a square matrix for this. I could have a more general thing with B, but in fact, for the purpose of proving the thing, I'll only need it in the case of two distributions on the same space. But I could do a more general one with B. I just don't want to, yeah. It just wouldn't be quite a permutation matrix, so I didn't want to get hung up over that detail. Then. E inverse. So basically, if I put a B here, they might be different sizes. So then what I should say is a permutation matrix. It should be basically, all zeros and ones. It won't be a permutation, but it would have to be a monomorphism. So I just, but in fact, for this, in fact, we could get away with just that case. All right. So that's the second property, and the third. Let's see. Oh, yeah, one. Oh, and the third property, and this is our third, I would say, subtle contribution, was to note that, if you do Bayes inversion twice, you get back the distribution you started with. And again, that's easy to see because, I have probably B over, I'm flipping, I put B over A, so of course if I do it twice, well, I transpose a matrix twice, I get the matrix I started with, and then if I have B over A times an A over B, that'll all cancel out.
Could you just say that again? So
I'm about to write it, yes.
okay, thanks.
And then, or actually, I guess, let's say beta. Yeah, so I have a matrix. So I first form the Bayesian inversion of that. And and then I Bayes invert again. I get back the original matrix I started with.
Right. Let me just ask one thing.
Yeah.
The thing above you assumes something square, that is to say the two sample
In
spaces.
this case,
are the
just to
same
make it
size.
simple to state, yeah. that's-
But of course, that also holds,
In this
it's
case,
a
it would have to
projection.
hold, here would always have to hold, yeah, here it
Right,
has
it's
to
a
be the same,
projection,
yeah.
yeah, got it.
Yeah, here would have to be the same.
Understood.
Well, no, here could be different,
Projection.
there could be different,
Could be, it's a,
there could be different ones here.
right, absolutely.
Because
That's
I
my
could go
point.
from one space
Right,
to a
right,
different
understood.
dimension
I
space.
just wanted to make sure, because,
Yeah,
yeah. whatever.
because I'm going to be transposing basically in these things so I can go between.
Absolutely.
So the E here does not need
I
to be
believe
square.
it. I believe it.
Here I just wrote in the square case for simplicity, and because that's all that's needed to prove the theorem.
Understood.
But one can, in fact, that would hold more generally, just a little harder to state.
Absolutely. That was my only, that was why.
And there's also a fourth thing, which turns out, isn't needed for proving a theorem, but Arthur notes is just a completion, is to say that if I have a product of sample spaces, then, the matrix I'll give you a tensor product, and retrodiction respects that too.
Right.
So there's that fourth part. Turns out, it turns out, as in the course of proving, at least for the base case, it turns out this wasn't needed, but since it was one of the, so this is a property, it's one of the ones that was already stated in Arthur's talk, let me, for
Yes.
completion, give it. Well, I guess alpha tensor beta. All right, so that's the,
Okay.
So, Ray,
yeah,
I'm told, I think I missed Arthur's talk, I'm told this was asked at Arthur's talk too.
uh-huh,
But,
uh-huh.
are the axioms you're giving, do they correspond to this being a dagger category?
Well, sure, yeah, I mean, because you could call the retrodiction type a dagger type operation, certainly, it's,
If it's not.
whether, okay, I don't know, yeah, I don't remember the exact definition of dagger off my hand, but basically the E, or is some, certainly an operation, I do it twice, it becomes the identity. So it's a functor from a thing to an opposite, so it might be so I think it's,
Yeah,
a
this
dagger
looks
or
exactly
something
like
close
dagger
to
to
it.
me, and that's what I'm
Okay, I
saying.
just
If
remember
it's
the
just
exact-
this, that it's
I-
a very strong
Yeah.
connection.
Yeah, I think that's correct, I just don't remember the exact definition of dagger off the top of my head.
Cool.
But if dagger just means, a functor from the opposite category to itself that squares to the identity, then it certainly satisfies that.
I think Arthur called it B for base,
Mm-hmm.
but he, at some point, somebody screamed out it should be dagger, and he said, yeah, it's a dagger.
Okay, so it is I just want to make sure I didn't miss some technicality.
But
It is a dagger, okay, good.
it's a nice definition.
Right, so point is that if I have, so points on this category, if I have a dagger operation that, let's say, it's the identity on permutations, then there's a unique, the claim is there's a unique one, and that's the Bayes inversion on this particular category. So there's only one way of making into a dagger category that preserves this condition, that where it happens to have those values on the permutations. All right, so we could say a little more about that, but I think that's enough, so I don't want to, I want to get to proof and not confuse matters with,
What, have you stated a theorem?
well, so the theorem is that Bayes inversion is the only operation that satisfies these conditions.
Understood.
So,
Understood.
first, yes, and Arthur's talk was a conjecture, and it was indeed a dagger category. Now I'm going to try to promote that to a theorem.
Okay.
So that's the purpose of the talk. So
I
good. At least
understand.
all right, so good. So that's good. So how to do it? So basically the idea is, well, I want to show that so what am I trying to show? I'm trying to show, so first of all, the history of this, by the way, I just mentioned before I get into the proof, was that, last October, Arthur gave that second talk. And basically, where he stated this, as I said, and then, well, didn't, suspect that Bayes would be unique, and that the quantum mechanical generalization of this would be unique, but didn't have a proof. Now, so I was trying, now as it turns out, this involves, these stochastic matrices. So I've been doing a lot of, basically in the course of what I do with theoretical biology, I've been doing a lot of, and Jay will know because he's, been on this
talked about this
adventure
15
together
years
with
ago.
me. spent a lot of time, in fact, talking about exactly this category, and I do a lot of things with that algebra of these matrices. So I was wondering, well, given what I know, this sounds like maybe I could prove it. So I spent about a week, and I came up with at least in a week or two, I came up with a first weak version. So if I assume that the operation is continuous, and here, well, because it's a function from matrices to matrices, so it assumes a continuous function.
I'm completely lost.
Well, I'm just saying, okay, let's say I make an extra assumption.
But it's already implicit in your,
No.
maybe I'm missing something.
No, this is purely algebraic, right? These are purely algebraic conditions. All I know is,
Sorry.
R is a map that satisfies
I
algebraic conditions. However,
Yeah.
I have know that a priori it's a continuous function. From matrices to matrices, it might,
Right.
And in fact, I can show you in a minute where you might go wrong.
Right.
But,
Let me just
Yeah.
restate this.
yeah,
So B is something.
Yeah.
And it's a topological space.
right,
Lies in a topological
Yeah.
space. A is something.
Yeah, or
It lies in a metric
Yeah.
space, actually. It
Yeah.
lies in something.
yeah,
And other than that, you haven't actually determined
Right.
anything about it. You're
Right.
not assuming it's a.
right,
it's
well,
a
that's right, all I have is the
column,
algebraic
stochastic
structure
matrix. Okay,
of matrix composition. I have the matrix,
right.
it's
You haven't
algebraic, so
assumed
I
that-
can-
you haven't
yeah.
assumed that
Right, but- yeah.
that the map.
I haven't assumed that the map R has any continuity condition.
I got you.
And in fact, in the theorem, well, it actually turns out that's not necessary. Continuity will come out in the interest, will
Got it.
come out on its own. But at first, I didn't know that, so I added that extra assumption.
Wait, this is actually a strong theorem, I think. I
Okay.
wasn't understanding it at all.
Well, let's hope it's at least a correct theorem. And let me try to convince you of that.
Correctness.
And then we'll figure out if it's strong.
Correctness is subordinate to strength.
All
I
right.
think that's another reason.
All right, so, yeah, so assuming, with the extra assumption of continuity, basically, turns out I'm basically dealing with automorphisms of a Lie group, I know about those, and so I was able to prove pretty quickly a version that there would be only finitely many possibilities. Then it turned out,
Wait, that's really good.
well, but it, yes,
I mean,
but
but that's
then,
really
yeah,
good.
but then a month later, I got the finite number down to 1, which involves a little bit of playing with convex things, as I'll show you in a few minutes.
What I look forward to is you telling me, under mistaken assumptions, what that number is.
1,
No, you have to drop some of your assumptions and then it's not 1.
well,
But-
sure, well, we'll figure out which ones to drop
Sorry.
later. We'll figure that out
Sorry for
later.
interrupting.
Right now, I'll keep all my assumptions
That's what
and
I'm
show that it's
interested in.
1. And then we'll see how much we're gonna weaken it later.
Right.
So, that's what I did, and then at that point, I started writing it up. I was still skeptical about whether or not you needed continuity, but, in the course of it, I found a way of eliminating it, which is at which point I got in touch with Arthur about this to let him know, and then, since there was an open spot in the category theory seminar, I decided to come tonight and present the proof. So with further ado, the proof. So, all right, so the first thing to do is, so what am I trying to prove? I'm trying to prove that a certain a functor satisfying some conditions is unique. Now, I'm ready, at least one of the conditions takes me part of the way there because it tells me that when I act on a very particular set of morphisms, I know that I told you the functor has to equal a certain thing. So it's obviously unique on these. So the strategy would be, well, I need to then look at all other morphisms and show that, it's unique on them. So how can I do that? Well, one way is saying, well, since it's a functor, so in other words, or I could rephrase the thing as saying I have 2 functors. I have my mystery functor R that satisfies these conditions. I have a known functor, which is the Bayes inversion. I want to show it's equal. I know there's some special morphism on which I, assumed it's already equal. But now since it's a functor, that means I only have to check they're equal on a generating set. So the strategy will be to say, well, I want to pick for this category of stochastic matrices, I want to pick some generators, and if I can show that it's, that the functor is uniquely determined on those generators, I know it's unique on the whole category. right? 'Cause it's a functor, all right?
Well, what's
So,
a generator?
well, all I mean is a subset of morphisms, such that any morphism can be
Written as a product.
produced, and that's, yeah.
That's the definition.
Yeah, yeah,
That's,
just like in group theory or
no,
anywhere
thank-
else in
thanks.
algebra.
Absolutely.
Nothing
I
mysterious.
just didn't know that.
No, that's all I meant.
Okay.
So, so the way I'm going to do is to start by saying, well, before I deal with the whole category, let me just deal with one Hom set. And in fact, I'll pick a very simple Hom set. So I'm going to pick, all right, so first I'll pick a 3-element, so for a set I'll have a 3-element set, and here I'll have the uniform distribution. So what that means is that, say A equals 1, 2, 3, and the distribution is just, gives me
1/3, 1/3, 1/3.
1/3.
Cool.
All right. So let's just deal with that case. Can I even do that?
Gotcha.
All right. Well, to make it, so what I'm going to do is, first of all, notice that I'm going to even simplify. So I'm going to, well, okay, I will do that, but let me just first say a few words about what the Hom sets, these Hom sets of look like. So I should have said that first. So what the heck does one of these look like? Well, it's some bunch of matrices. So which matrices? We can think of it a little geometrically. So basically, as I said, there were matrices that be matrices of positive real numbers that satisfy, that preserve the normalization. All right. So let me just take a moment to just say what that looks like, give you a geometric picture of that, so we can at least get a bit of a break from the algebra with some geometry. So let's say I'm dealing again with in this case, I've probability on 3 elements. So I have a sample space of 3 elements. All right, so 1, 2, 3. So as I said, what is a probability distribution? Well, it's an element of R3 that all the 3 things have to add up to 1. So that means it's gonna, let's say if I put 1 here, it's gonna sit inside the plane determined by this. However, to be a probability distribution, all its elements have to be, be positive. So now that we point out, so it's not just any arbitrary linear combination of these, 3 unit vectors. It's going to be one that lies inside this triangle in the plane. So that's where the plane is locus of things where all x, the 3 coordinates add up to 1, and they're all positive. And so it's this triangle, or in general, it's a simplex, the so-called probability simplex. And this would be something that spent a lot of time with Jay in the past on. All right. So now,
And the other 6 people whose names were on it, my name wasn't,
Yes.
but yes.
yes, right.
Okay.
Well, of course, yes, and Cameron.
Right.
All right.
And Aviv, of course,
And Aviv
he was critically important.
Yes, sure. All right, so anyhow, so that's this. So now, so then I have a particular probability, well, that's just a point in here. Let's say this uniform distribution might be, this point in here. So that's our, all right. Now, what I want to do is to say, now, suppose I have, let's just say even mappings from, this thing from the same sample space to itself. So that's a linear map that basically, of this plane that sends this triangle to a subset of this triangle. So first of all, if I don't worry about the positivity on triangle, what is the space of all mappings that given a plane will send it to itself? Well, that's going to be our group of affine transformations. So, which in this case would be, let's say, all right, let's say 2, because it's a 2-dimensional thing, it's a plane. So I just mean homogeneous, so that means in addition to the usual matrix, I have a translations in there. However, if I require that it fix, say, this point alpha, then I get a subgroup of it, which is just GL of that. Basically, because, I'm talking about affine transfer plane, but once I pick the point, well, that point, so to speak, becomes my fixed point, that becomes my origin, so I only have the general linear group. So I'm doing that. But as I said, what I actually have, so the thing I'm after is HOMs are things that have to, map the triangle into itself. So they have to preserve positivity. So that's actually going to be a subset of that. So let me just write it like this. So that's going to be some subset of this thing. All right? And however, being a HOM telling itself it's a monoid. But point is, of course, this is a group, and that's a monoid. And it turns out that this monoid sits inside this group in a special way. Namely, so I'll just, I'll just cite the result and stop me if you want to say more. But it turns out that if you look at either this group or this monoid, they have a non-trivial, they have a center.
They have a what?
A center.
Uh-huh.
A subset commutes with everybody.
Right.
Because as you know, if I have a general linear group, well, all the diagonal matrices are the center of that. They commute with everybody. Right? So diagonal. Now, furthermore, I can, and in fact, by the way, in terms of the probability distribution, there's a nice way of visualizing this. What these things as central are. So here, let's say I have my, probability. So here's my probability simplex. Here is my preferred point alpha. And in fact, these center things are just where, given any point, all I do is I basically just shrink it uniformly into that. So let's say what I want to be center, for every point in the simplex, I just squash it by a factor of 2, keeping alpha fixed. So I would say, flip that, let's say, so we map the whole simplex down into this triangle of half the size, for instance, or whatever fraction. So it turns out that if I raise the matrices, those are the center of this group. All right. Furthermore, basically I can find out that given, now suppose I want to go from the monoid back to the group, or rather, well, take the all the non-singular matrices in the monoid. Obviously, if they're singular, I can invert them, they'll knock them from the group. But if they're non-singular, turns out all I have to do is just invert these central things to get that group.
Say it again, please.
All it turns out, if I just take the monoid,
Right.
so let me slow down. I take my monoid, well, I take the submonoid of the ones that are non-singular.
Sure.
So let me say let's say M is going to be the non-singular things from the non-singular ones.
These are still required to have positive entries
Yes,
in the matrix.
yes,
Understood.
yeah, M is the monoid, so they're required to have it.
The non-negative, yeah. Okay, sure.
Right.
Sure.
So then the statement is that actually, if I want to go from this M to the whole group, all I have to do is invert these diagonal ones. So just the local, I'm trying to invert or localize the thing, and first statement is that just doing these is enough to do that.
No,
Sure.
the HOM shouldn't be in GL, right? Because
Well, let's see. So I think the HOM is, it's a map from as a matrix map from probability space to itself.
then that might not be.
Oh, it's not the HOM. Okay, you're right. So, all right, let me put it this way. The M is in there.
Yeah.
You're right. Yeah. You're right, so strictly speaking, it's exactly
We
exclude
just
the.
take isomorphisms, right? Isn't that the same thing?
Yeah, well, but the point is I don't need all the isomorphisms. The only ones I need to add to invert are the diagonal matrix.
Oh.
So of course, if I inverted every isomorphism, I get the group. But the thing is, yeah, if I take M and I just adjoin to it the cop R, that generates the whole GLN. So that's maybe a quick, so M, R as the diagonal guys. So that means given any non-singular matrix, I can write it as, so if I'm given any element of, or another way of putting it is, yeah, I'm given an element of GLN, I can write it as, some element of M times some diagonal thing. So I have that factorization. And let me just, again, so I don't make a mistake here. Central morphisms, blah, blah, blah. Yeah. Right, that's it. Yeah. So it's there. Sorry, I just want to get this statement correct. Yeah, that's what I need. So for all. Oh, is this too low?
No, that's perfect.
Okay, good. I'll just write, I just want to write the statement of this here just to make everything clear. Every E. All E in M. I've got an F. Then let's say that's way, okay. Who's some. So there's where this is. Yeah, I'm sorry. Oh, right, E, let's see. Okay, fine. And I've got the F matrix. Let's see if I got the right token backwards. E in linear, yeah. Yeah, that's right. F is in, yes, that's fine. So yeah, given any, in fact, any GLN matrix, and the intuitive idea, if I had an arbitrary thing, what could go wrong? It could map my triangle into something whose vertices are outside here. But then my special transform shrinks everything back. So if I shrink it enough, I get it back to fitting inside the triangle I started with. So intuitively, that's why I can do this.
Okay.
Now that's useful because that means, you see, with my retrodiction, if I restrict retrodiction to, first of all, to slight technical point, I can check that if the matrix is invertible, its retrodiction would also have to be invertible. And basically the reason for that is that if something is invertible, I can, as a matrix, its inverse may not be a stochastic matrix, but I can certainly, it can certainly cancel it against anything. So basically using that fact, I can show if a matrix is not singular, its retrodiction won't be singular. And then using this fact, I can actually then say that, retrodiction isn't just, a morphism, of this monoid M into itself, and in fact generalizes to a matrix homomorphism of GLN to itself. And now that's useful because for GLN, we know what all the automorphisms of that are.
Yes.
So, well, assuming continuity, there are only two things that it could, that basically an automorphism of GLN turns out to be, well, on the S, okay, let me just write what it is. So it's basically, so automorphism of GLN turns out to be a map that it's either take M to M times some power of its determinant, or take M to, again, power determinant, but times the inverse of the transpose of M. Those are the only automorphisms GLN has. So if we assume continuity, we knew our retrodiction in the special case of where I'm mapping the same thing into itself would have to reduce to one of these two things. Furthermore, what do I know? First of all, I can exclude this because basically if I'm taking an inverse, my retrodiction has to also, I said, be also map, the triangle into the triangle. And if I invert, basically take the inverse here, I want to send off things to infinity, so there's no way this could be possible. So I could basically just rule that out. Then furthermore, I have, now then the question is, well, okay, here I've got this arbitrary power, what would that be? Well, we can now use this condition, the dagger condition, that when I do the retrodiction operation twice, I get the same thing. So because if I multiply, the matrix by power of the determinant, then repeat that operation, well, I'm going to get twice that power. So the only way I could get the same matrix back was if this power was equal to 1. So in fact, so the fact is that if, let's write down, so for that to, do it twice to get the same thing, that must imply that this power is 1. All right, so the question is, so assuming continuity, I got, at least that's the first case of my result. Because I'm, claiming, yeah. So I do this, well, okay, so I should, let me say that, well, okay, so this would be, okay, there was actually, okay, so let's just say in the case where I had this with the uniform distribution. So I have the uniform distribution on both sides. Well, if I have the same distribution, basically the point is that if I have the same distribution, if these distributions here were the same, right, then obviously this factor would cancel and my Bayes retrodiction would just amount to transposing the matrix. And I claim because of the argument with the thing, so I guess, okay, so what I should say, that's an ordinary automorphism, but our retrodiction was, contravariant. So really I should say, so for retrodiction, I should say, really, it should be either m goes to, determined to a power times m transpose, or the retrodiction R would really be matrix to a power times m inverse.
So did you, maybe said that there was the continuous automorphism?
Well, if an automorph, if I have an automorphism GLN, and it's continuous, then it must be only one of these two things. But if it's not continuous, it need not be this. Basically what I can, see a problem is, if I don't have continuity, what I can do is, let's just concentrate on the case of GL1, so the real line. Well, as you know, the real line, if you think of a vector space over the real number over rationals, it's got a, it's infinite, uncountably infinite dimensional. And if all I say is it's an automorphism, that I can separately, on each basis, on each irrational number, I can have it scale it by a different amount. And therefore come out with all kinds of crazy things that don't get this at all. But I realized that the fact that I have to map this triangle into itself is enough positivity to rule that out. And so let me just quickly indicate how that works. It'll take, so basically it goes back to just using it. So let's look at the simplest case. And in fact, one can then bootstrap from the simplest case to the full case. So let me see okay, I'll erase something. I guess I'll just go back over the red thing. Who cares about that? No, bother that. What's in my other hand? Okay, I guess I'll just erase this definition. So let's just, in this case, and I've taken a while. Once I do the simplest case, it'll be quick to sketch the ideas and the rest of the proof, and leave the algebra for anyone who wants to read the notes. So, again, this is a talk. I just want to focus on the main ideas, not all the details. So by the way, just for a reference, this is something I finally got into a final simplest form after staying up to 4 in the morning last Monday. So if I'm a little bit dizzy, you'll know why. So just get the... Yeah, my lemma. Where's my lemma? Oh, there it is, yeah. So, so let's just say basically the simplest case of what I'm saying with GO1. So I want to have a map. So let's say, what does it mean to have, first of all, an automorphism? So let's just take GO1, let's just say, it's the multiplicative group of the real numbers, but by taking a logarithm, I could make that just additive group. So let's just say, automorphism over additive group of real numbers, all right? So what does that mean? Well, means I've got a map from R to R with this property. Right. So it's a linearity thing. So obviously I know, that's going to be linear over rational numbers. So that means if it's a rational number, because that's just, follows from this purely algebraically. But as I said, in general, it need not be true for irrational numbers if I don't, make an extra assumption like continuity. However, in the case, of where I want to apply to probabilities, I did have an extra assumption in that it needs to preserve positivity. So, so let's say you make the extra assumption that if so suppose I just say that it makes one extra assumption that it maps the positive real numbers into the positive real numbers. And then I claim that's enough to actually show that this thing is, linear over all real numbers. And basically one way to prove that is you go back to construction, construction of real numbers and cuts. And so the idea is to note that, well, suppose that, x is bigger than 0, right? So as usual, we know that there's going to be, we can put x, we can approximate x as close as we want by a rational number. So for example, let's say, okay, fine. Right, so let's say, x is, so say x is, bigger than some rational number, all right? Then I can show that, well, basically, so what I do is so all I have to do is show that, in fact, what's even simpler. So make this one assumption. Now I'm going to note that actually forces f to be monotonic. Why is that? Well, assume that, so let's say I have two numbers, x is bigger than or equal to y, bigger than or equal to 0. Then I'll notice that, then from this assumption, well then I'm going to say, then let me look at what is f of x minus f of y. All right, well, I'm going to write it as so write y as y plus x minus y. Now why did I do that? Well, I said x was bigger than y, so this is also going to be positive. Right, so that's positive. And I assumed y was positive. Oh, but I told you when, but now, so I have two positive numbers, so now I know that, and I know that for positive numbers, f satisfies this equation. That's my hypothesis. So I can write this as I can add them up. And then, of course, I can just cancel. All right. But what is this thing? But I also know that when the thing is positive, this x minus y is positive, f of that has also got to be positive by my assumption here. All right? So what have I just shown? I've just shown that in that case, if x is bigger than y, then f of x minus y is also, then f of x minus f of y is also positive. So in other words, it's a monotonic increasing function. And basically, you know, if you just think about, well, think about, you know, how you use your Dedekind-McNeil or Dedekind-Cutts to get the real numbers. Basically, we know that the monotonicity, you know, when you take your rational numbers, the only way to complete that as a monotonic thing, or as a lattice, in order to preserve the monotonicity, is to go to the real numbers. So basically, for that reason, then, if f is monotonic, the only thing that would do it, that will make it continuous.
I believe you have a proof, so that's the.
All right.
I haven't been followed.
All right, but that's the whole point. Well, proof is simply, I noticed that, you know, any map under this condition, my f not only satisfies identity, but it must be, you know, monotonic on the rational. Hence, it will extend uniquely to a continuous function on reals. So in particular, I get my continuity out, and hence I can, you know, and then using this, so this is the simplest case, where I had, you know, let's say, you know, just, well, real line, which I could think of as GL1. But I can bootstrap that up to the GLN. And basically, the way I can, and I won't go through detail on, but the basic idea there is that, let's say I wanted to go up to this, well, this GL2 thing here, these 3x3 matrices. Basically, I can find myself a subgroup of them that's, you know, isomorphic to 2 copy R times R. So just a 2-dimensional, you know, a subgroup. All right, let me just erase and just write a letter or two for what I was saying. So maybe I shouldn't have erased my axioms, but so be it. So all I'm saying is now, suppose I was looking at, you know, say GL2, which I'm thinking about these as these stochastic matrices. Well, basically I can find, you know, 2-dimensional subgroups. So if I take the matrices, for example, well, diagonal matrices are a commutative 2-dimensional subgroup. And then basically, you know, commutative subgroup is isomorphic to R cross R. So by using that fact, one can show that, well, on that subgroup will be continuous. And furthermore, I can generate the whole GL by permutation matrices and this diagonal thing. So if I have, yeah, so let's say, for example, so generated by some commutative subgroup and the permutation matrices. All right, and basically, all right, and because, you know, in the axioms I just assumed, I just erased, I assume my retrodiction would turn the permutations into themselves, then, you know, knowing, all I have to tell you is what it does on the commutative ones, and then I can basically use this argument. So I showed that it's, so I showed that the thing is, you know, that my retrodiction, my function R is actually continuous. And therefore, once I've shown that, I can then use, you know, the answer that I already knew in the special case when it was continuous. All right, so that's that. Now let me just quickly then, so basically doing that, I can take care of the special case of these square matrices that send, say, a uniform distribution to itself. So using the arguments I just did. Now I'm just going to, in the last 10 minutes or so, then tell you how from that you go to showing that it, on all the stochastic, so the full category, not just this sub-monoid of square ones, it actually does what it does, it's actually unique. All right, so the idea is very simple. Let's say I've assumed it, so I know, let's say so now, so include that, the restriction, you know, let's write it this way, so, all right, so let's say U is, I'll just say, right, U means here the uniform distribution. So the uniform distribution is going to be E transpose. So here I mean where E comes from some fixed set with the uniform distribution. All right. So it's a transpose, which is the same as the Bayesian in this case. All right. So so we can conclude that, as I said, by this kind of argument that I mentioned, of saying I look at, all right, I know that's generated by these commutating and permutations. By my assumption, the retrodiction will just send the permutation to its inverse, and inverse of a permutation matrix is the same as the transpose. And on these commutative things, I make use of this argument that the commutative, all right. So I've shown that. Now, what if I wanted to consider instead, say, I want to generalize it up to something where these aren't the uniform distributions anymore. So I can do that in two steps where I replace one of the uniform distributions with an arbitrary one, and then here. So let me just show the main idea behind that. All right. Just copy what I had there. So the idea is I want to look at a mapping from who I want to use. And you got it. Okay, and uniform. Okay, I want to put the uniform thing here. So I'm going to look at the case where the domain guy still has the uniform distribution on it, but the codomain may be arbitrary. And yeah, we can start with, so what's the idea there? Well, what I can do is basically say, well, I could write my matrix as, pick any matrix that does this, pick a particular one. And then, so let's see how does this. Okay, see how to say this. Sorry. Yes, I want to say a factor. Let's leave that nonsense out. Who I want to look at? Sorry. Yeah. Yeah. How did I define that? Right. So then, yeah. So I want to show that. Okay. Right, so that's right. I'm going to write it as A, from there, A there. So what I do is I'm going to just pick some fiducial, F for fiducial. So F is also a matrix that maps same place. It takes same thing, it sends a uniform, to beta. All right, and let's say it's an invertible one. So there certainly are such. So let me just pick one. Pick an erroneous. Any other matrix E of that form can be written as, okay. All right, let me change, that's okay. Call it the fiducial one, this way. So any other matrix I can get by composing it with some matrix that sends the uniform to the uniform times this fixed f. All right, just simple linear algebra. Now, then using the fact, but now using this and what I, by fact that my retrodiction is a functor, I can then say that the retrodiction under a uniform matrix of E will equal to, okay, got it, to retrodiction of of F, just the property that E is a composition of them, so except I can composition.
Do you want G to be invertible?
Let's see, well, wait a minute, so F was invertible. Yeah, so let's say this was in fact, let's say that the case the same, so I have just revertible for now. So then F is in, so points, even if I have an arbitrary G, basically E is just, all I'm saying is E is just, G is just E times F inverse, because F is invertible, that's all I mean. So I just define extra symbol, I could just written as E times F inverse, maybe I should just written it that way. In fact, yeah, words, right. So point is, yeah, that's right. In fact, let me just write it that way.
Okay.
So E is, E is going to be, well, E times F inverse times F, and I do it this way. So point is, this is a fixed matrix. I fix, given the state beta, I just pick the matrix F, I fix it. As I let my E's vary, I'm going to leave F fixed. So that's fixed. But this, you see, so then, yeah, right. But since this thing goes from uniform to uniform, I already know what retrodiction of that is. It's the base. It's already determined to be just the transpose of it. I mean, that's using the result, because I already showed the result when if it sends a uniform distribution to a uniform distribution. So now I'm saying if it sends a uniform to anything else, well, I write it as, pick one thing that sends it, write anything else as that times the inverse, and I can do that. All right, so I've gotten basically, so for each such state, I've got a matrix F, and I just have to figure out what this matrix is. And so now, the way I do it is basically, okay, so I'm gonna skip ahead and then stop me so I can figure out what I need to fill in. So what I notice is that basically, just give me a minute to think the best way to think. So this is where I'm going to have my, it's basically my convex business with the, all right, now it's a polytope to a polytope, right. So basically now I'm going to use the fact that, well, let's say let me even leave this on the side for a moment. I'll get back to this equation in a minute. But well, what I'll take from this equation, that obviously this is a linear map on E, right? As if I put the matrix in here, I'm just taking, transpose multiplied by some matrices. So this map tells you the retrodiction of E is given by take some fixed matrix times the transpose of E times some other matrix. Or in fact, let me just, so yeah, in fact, let me just write that down one more time. That's right. So whatever this thing is, times F inverse transpose times E transpose. So it's telling me that if I have a matrix that goes from uniform distribution to any other distribution beta, to that distribution beta, I have some matrix where retrodiction is given by transpose E and multiplied by that matrix. Now, comparing it with the original definition of Bayes' rule, well, Bayes' rule was, given by transposition times multiplying by something, but the thing I multiplied by had to be the ratio of probability distributions, which in other words would mean I have to then show you that this thing happens to be the diagonal matrix. If I do that, I'm done. All right, so how can I do it? Well, this is a linear map. Now, the space of all matrices, as I said, that map, the probability simplest into itself is a linear space. All right? So the probability simplex itself is a, convex thing, simplex or triangle. But then if I ask, well, what are all the stochastic matrices, namely the matrices that map one probability simplex and another, in this case, also map the special point of each into it, that also is a convex space. Because, why is that? Because it's, well, just given by the conditions are, there's a linear on the matrix are that the rows have to all sum up to 1 and all the entries are positive. So saying that components of rows sum to 1, that's a linear equation. And saying they're greater or equal to 0, well, that's a linear inequality. So anytime I have something defined by linear equalities, I get a convex shape, convex polyhedron.
Mm-hmm.
So I have some convex polyhedron. And this is a linear mapping. So if I have a linear mapping of a linear space that sends a polyhedron to a polyhedron, and furthermore, we know it actually has to map the whole polyhedron to whole polyhedron because of the fact that the thing is its own inverse.
But don't you also need that in stochastic?
Well, yes, I use the fact that it's stochastic.
Right.
Yes, stochastic, so that I'm saying because it's stochastic, the space of all stochastic matrices inside of, let's say, n by n stochastic matrices, it's a convex subset of Rn cross n. So I should perhaps, let me write a little bit down to help anchor what I'm saying. So, point is that, so my thing that I'm calling my, let's say, just using my notation. So again, this was all the stochastic matrices that, A by side, cardinal of A times cardinality B stochastic matrices that send a particular distribution alpha to a particular distribution beta. So that thing, first of all, I said I can think of it as a subspace and, R cardinality of A times cardinality of B. But as a subspace, it's characterized by linear conditions. Namely, I have a linear, that the rows all have to add up to 1s, that it has to set alpha to beta. Those are all, beta, the sum of those are all linear combination. And then I have an inequality that each of these things has to be bigger than 0. So it's a subspace of an Rn that's defined by some linear equations and a linear class. So that it's going to be some kind of a convex polyhedron.
Mm-hmm.
So not like this one, but something like that, some convex polyhedron. Now, what my retrodiction is a map that sends one of these into another one of these. Well, it sends from alpha beta to the beta alpha. So what that means is that has to be a map that maps this polyhedron into itself. And I do a map twice, I get the identity. So furthermore, I showed that it's actually a linear map. So the only way I can have a linear map of a polyhedron into itself is if I send all the vertices back into vertices, edges into edges, faces into faces. And then So it has to send them into themselves. So now, the problem, so I have to do, so first of all, that's why I was saying I got things cut down to a finite number of possibilities very early on, because this polyhedra is only going to have a finite number of edges and faces. Unfortunately, it's a big finite number, and of course, the bigger n is, the bigger it is. So, that still leaves a lot of possibilities, but at least it's a finite number of possibilities as opposed to potentially continuous, infinite number of possibilities that I started with. Now, how can to finally pin it down and show that, and I want it to be basically the identity transform. So how do I get that? So what I have to do is actually, to check it on, so what I can do is if I could identify some faces or vertices and check it on them and show that it indeed, what it does on them is the identity, then I'd be done. And so the way I did it was like I said, well, potentially this thing could be quite complex, commutator. However, I figured out a tricky way, a simple way of getting enough faces to do the job. So a face, of course, is going to be given by one of these conditions, where one of these things is bigger than 0. However, not every such condition needs to give you a face. Why is that? Well, it's quite simple. Let me just give a simple drawing to illustrate what the potential problem could be. Suppose I had, one inequality was, let's say, picked out this half plane. The next one picked out that half plane. So I got this. But then if my third inequality I tried to add was this one, so I wouldn't generate a new face because I already have, these two things as faces, but this isn't giving, no point on this is a face because it was already excluded by a previous inequality. And so that's the problem. So I have to find, so that's where it becomes so the tricky part is, so I just have to be sure I get something which, explicitly really is a face, not just any one of these things. And so the way I do that is quite simple. I basically say, given, well, let me just finish it now. Done, positivity, yeah. So what I observe is the following, So take on my distribution alpha. And I'm going to have a distribution, and well, it's going to have, of all the probabilities in there, one of them is going to be the smallest. It may be, there may be a tie for the smallest, but pick the minimum. It doesn't have to be unique, it just has to be a minimum. And then, all right, so yeah, I is so let's say J, so let's say there. So alpha J is less than or equal to all the alpha i's. That's alpha 1. Okay, now, so what I'm going to do is look at a matrix where, consider a set of matrices where Eij is 0. And I just explicitly can write one down where in fact the only non-zero entry is Eij. So I can find one where Eij is 0 for any j, for any I rather. So for any I have, so I matrix E such that Eij is 0, but every other entry of the matrix is non-zero. So it's got, so it has a 0 here, but everything else is non-zero. And basically I use the fact that I picked J to be the least, to be the smallest one of these, and then and I just construct a matrix out of alphas. So I have to have them add up to 1. So basically, since it's the smallest one, I know if I remove it, and I rescale it, I can get everything equal to 1. So all the columns add up to 1, and it will send alpha to beta, and it's just simple algebra. paper I write down of explicit formula, you can just check it. So what does it mean? Well, first of all, the only non-zero entry of this matrix is the ijth entry. So in other words, it only satisfies one of these inequalities. And if you think, by that way, that means that must be a point on a face. Because if I was out here, well, every point here would have been excluded previously. So I've got a point each face, and in fact, I have n points on n different faces. And those are basically, those faces are, well, they're basically linearly independent of each other, so using that, that's enough to do a bit of algebra and determine what that, that thing must be the identity. That matrix must be diagonal.
I have a question. Are these points basically the edges of the shape? I mean, sorry, the
Yeah.
vertexes of the shape?
Well, no, actually, there are points on the inside of each face, like here.
Okay.
They're not the vertices. First, I tried to find the vertices. Trying to find the vertices in general, I don't know what it is. Maybe some combinatorialist, of the caliber of Stanislavski could figure it out. I can't. I am not that. But I just noticed that I can find inside of each face, I can find a point in the interior of each face by this trick.
Okay.
By say, pick the smallest thing, the probability screen, I just explicitly write down such a thing. So I write that down, and then
I think we should,
I'm wrapping it up. I'm
okay.
near the end.
Okay, good.
So I'm saying, with a little bit of algebra, then you basically show that given, I know what those points are, so those point faces must map into a face. So from a point of that, the point is that I know that since I have a point on a face, I know I have a face here. And so in the vicinity of a point interior face, I'm going to have, some neighborhood that's in the face, and hence I can pick a basis of vectors there. And then I just see how they, seeing how they map here, showing, and I know the face must map to some other face. And so I say, okay, every point there, so I take this matrix with zeros, I write down what it means for a face to map into another. So in other words, all the matrices that have a zero at this ij location must all map to matrices that have some other entry all zero. That gives me a bunch of conditions on them, algebraic conditions on matrices. I solve those matrices, and that tells me that actually the thing here that I write my retrodiction as a multiplication of something times it, this must be diagonal. Then I do a little bit of more work with the permutation matrices to show that this is not only, so first of all, this is shows that this is a permutation matrix. But it turns out you can also show it must compute with all the other permutation matrices, where basically the only one permutation matrix that computes with all permutations in 3 or more dimensions is the identity. So that forces this to be identity and tells me that yes, the retrodiction is always the Bayes retrodiction. So that's the base idea. As I said, there's plenty of algebraic details in this, but I tried to at least get some of the main ideas across. And I hope I succeeded.
Questions? And just, what's going to be the hard part, within 3 minutes, what's going to be the hard part about doing this for quantum?
Oh, well, first for quantum, okay, so what's going to happen is that here I had a GLN.
Right.
So here I'm going to have, right, so for quantum, the analog of this would be, instead of stochastic matrices, I have something basically that preserves density matrices. So it's going to be some, instead of stochastic, it's going to be some generalization that includes unitary or whatever. Right. So the question for me, what I want to know is, well, what is that extra, first of all, what is that group? It's going to be some, it's going to include GLN, it's going to include unitary, what is it? And then you could try doing the same thing and say, well, if I looked at automorphisms of that, what would it be? But I haven't done it, and I'm not even sure what exactly the group is.
Right.
But presumably it would be just that. That would just be the issue that, yes, instead of a GL, I'd have some otherly group that obviously includes, it's a complex thing, it's going to include unitary matrices in there, because this is not just a unitary matrix in quantum, this would be things that preserve density matrices. Because he's dealing with mixed states, not just pure states.
Right.
So whatever the analog of a stochastic matrix is when you're acting on mixed states, that would be the category, and each set of monoid of that would be, subset of some league group, and I guess the question would be which one. I haven't even started looked into that.
But it's on the agenda.
That would be the next thing to do,
Right.
obviously next step after tidying this up.
Very nice, very nice.
Yeah.
Anyways, thank you.
Thanks.
Next week, Emilio, you're speaking next week, right? On profunctors, presenting profunctors. Very
We
nice.
saved the best for the last.
No, there's one more talk afterwards, but
Oh,
somebody, well, he hasn't given me a title yet, but
oh, okay, there's.
anyways, thank you very much.